Today, I'm excited to be introducing you all to this new problem that we established called hardware decompilation. We've adapted some PL techniques to the world of hardware. So we've adapted some techniques from PL to the world of hardware description languages to solve that part of that problem. So first off, I want to talk what is hardware decompilation. So this is this problem that we established in our work. It is analogous to software decompilation, where you would take an executable binary, lift it back up to source code. But in this case, we're dealing with a netlist. And so a netlist is an artifact of hardware design. It represents a digital circuit at a low level. So we want to find and recover higher level programming abstractions and generate code written in HDL, like Verilog, PLDI'23, Chisel, and so on. So why would we want to do hardware decompilation? Well, there's a number of applications that we can come up with. Some similar ones, like with software decompilation, like understanding and analysis in situations where we don't have access to source code. But we do have some surprising kind of non-nefarious uses for hardware decompilation. And I want to get into one of those in particular. So let me start off by saying, imagine if your compiler produced something that was not equivalent to your source code. Well, that is kind of the everyday life of a hardware designer. When we take, say, our Verilog code and we put it through logic synthesis, it lowers your hardware description code out into a netlist. And this basically flattens everything, ungroups everything. And the way that these tools work is they can produce something that is not always equivalent to the code that you have, right? And so what a hardware designer has to do is they need to take that netlist that their tool produced, and they need to run some simulations on it for functional correctness. Now, the issue with this is that simulating over a netlist is really slow. Like I said, we've taken all that structure, all the hierarchy that we had in our source code, and we've flattened it into this big graph. So simulation is really slow on this. So if we had a hardware decompiler and we lifted that netlist back up to the HDL level, we can actually speed up simulation time. And this is something that would be really valuable in the hardware design process itself. Another thing I'll mention here is that dealing directly with netlists is pretty common in the hardware design process. Hardware designers often deal with a lot of third-party intellectual property. They don't have access to the source code. They have to deal directly with the netlist. Okay, so there's a number of different abstractions that we would love to target with a hardware decompiler. We can think of things like loops, functions, modules, state machines, lots of things like that. And so what we're focusing on in our work are we're recognizing repeated logic in these netlist graphs. We want to decompile them back up into loops. So we found that loops are a good first step for a hardware decompiler. And so we want to take that, lift it back up to a for loop in the HDL code. All right. And we call this hardware loop rerolling, which is kind of mirroring a similar operation in software, where there's loop rerolling in compilers. But we're doing this in the context of a hardware design, which has kind of a different execution model than software, so the techniques don't really translate over. So we came up with our own technique. So first, I want to introduce a little example to motivate this. Here is some SystemVerilog code that describes a 4-bit accumulator. It's this 4-bit register. Every cycle, we get this input, and we add it to our register. The way that we do that summation, the add operation, is through this n-bit adder that we have here. So we instantiate that n-bit adder with a 4-bit bit width, and the way we do the actual sum is through a for loop. This is a pretty standard way of doing using a loop to do an add operation. Right? So the body of the for loop computes the add and carry operations for the whole sum. Now we take this SystemVerilog code, we put it through logic synthesis, we get this netlist. Right, this is a graph that kind of blows up the code that we have. And so what we want to do is, if we look really close, we can kind of see groups of repeated operations in this graph. And what we want to do is find those kind of contiguous blocks of repeated operations, lift them back up into loops. So our solution to this, to the loop rerolling problem, is to break it down into 2 subproblems and adapt a different PL technique to solve it. And so first we have loop identification. We want to find potential candidates for loop rerolling. I adapt some techniques from software clone detection to do this. And then once we have loop candidates, we want to actually re-roll those into loops. Okay? And to do this, I adapt CGIS-based program synthesis techniques. So in this talk, I'm going to go over how we tackle hardware decompilation, focusing on hardware loop rerolling. First, going to introduce an IR that we use as a common connecting format between the two phases, and then go through how we do loop identification and rerolling. Okay, so for this problem, it made sense to use some kind of intermediate representation. We need some kind of language abstractions that sit between the low-level world of the netlist, that big graph, and the higher-level world of a full HDL, and we want to be able to reason about that in the same language. Okay? So I developed an intermediate language called Maki that can fully specify a netlist before decompilation, but it also contains abstractions such as loops and arrays that we use for loop rerolling. So this is that netlist, that 4-bit accumulator in our Maki IR. And this kind of looks like this sort of SSA form IR, and it is an SSA form in this way. At the top, we have some port and register declarations, and the main body here are these statements. And these statements are kind of a one-to-one translation from those nodes in the netlist graph. So these are all different wire operations, and we just declare these intermediate wires for each one, and so we can directly translate a netlist into this sort of SSA form. Maki programs describe one cycle of evaluation, so when we have things like stateful elements like registers, we kind of figure out what their new value should be and then update it at the end of each cycle. Maki is constrained in this way that it only evaluates hardware designs in a single synchronous clock domain. The full semantics, or the semantics are in grammar are in the paper as well. And I'll introduce some other features as we go along. So now that we have our netlist translated to Maki, it's in this kind of SSA form. We want to do loop identification. Okay? And the way that we do this, like I said, I took inspiration from software clone detection. In this case, a clone is some repeated segment of Maki code that's identical to some other segment. Specifically, we're looking for clones that are tandem repeats. So these are sequences of kind of consecutive clones. So the process is actually pretty straightforward for identification. We're going to tokenize and abstract the Maki program coming from the netlist, and then we do a tandem repeat analysis, which is this kind of standard sequence analysis. So this is that example after we tokenize and abstract that 4-bit accumulator netlist, do tandem repeat analysis. This one is fairly small. We can visually see where the tandem repeats are. And when we do this for the whole netlist, we get back all the different loop candidates, how long they are, and the number of repeats. So now that we have all the different loop candidates from identification, we want to actually figure out, can we reroll these into real loops? Because we do a bit of an abstraction over that token stream, we're kind of over-approximating the number of candidates, but that's what loop rerolling is for here. Okay, so what's a naive way that we could do this? Well, we could take one of those tandem repeats and just kind of like wrap it into a for loop, right? Just take one iteration and do that. Of course, this is not going to work. This is going to break the program. Like, it's not going to be semantically equivalent to the netlist because we've broken a lot of data dependencies now. And so the way that we decided to solve this is by doing program sketching. Okay, so we take this sort of a single iteration of the loop, a single iteration of that tandem repeat, wrap it in a loop, but we're going to start poking holes in all the different parts inside the loop and before and after. And the way that we do that is by doing some fairly standard data dependency analyses, like reaching definitions and liveness analysis, and this will kind of introduce a bunch of holes, add some new statements in a way that will fix all those data dependency issues, and we have a loop that is, or a rerolled loop program that's equivalent to the netlist. So the question is, how do we fill in these holes for these sketches that we generated? Well, we reach for some program synthesis techniques. So we use Rosette, which is an established framework for solve-related programming, and we implemented an evaluator for the Maki language in Rosette. And so by doing this, we can now symbolically reason about Maki programs, these hardware designs, and we can conveniently use that original netlist as an oracle for all the different program synthesis and verification facilities that Rosette has. And we'll be able to find some satisfying solution for these holes. The details for sketch generation are in the paper. I had to kind of skip over some of the details there. So this is that sketch that we had with all the holes filled in. using Rosette, we were able to prove that this solution is identical or semantically equivalent to the netlist, and we can directly translate that to SystemVerilog. And if we squint, that looks pretty similar to what we started with. Okay, so how do we evaluate this? So what we did was we built out 2 suites of benchmarks, totaling 53, and those suites covered 2 HDLs, SystemVerilog and a Python-based HDL called PLDI'23. The SystemVerilog benchmarks were all drawn from the BaseJump standard template library. We chose that because it kind of represents a lot of different common hardware components that you would normally find in the wild. To summarize, we re-rolled loops in 52 out of 53 of these netlist benchmarks. We had a timeout in one of them, which was the largest benchmark in our suite. And we often found that we re-rolled more loops than were in the original source code. There's a couple reasons for this. I'd be happy to answer any questions about that, and the details are in the paper, but I don't want to take too much time. The other part of the evaluation that I want to emphasize here is simulation. So I kind of motivated that speeding up simulation is a good application of a hardware decompiler. And so what we did was we took that original netlist and the re-rolled code from loop rerolling, and we compared their simulation speeds side by side in Verilator. In our benchmark suite, we found that we had a mean speedup of about 6x, and in one case, we had a max speedup of 30x. And so, again, this is one of the motivations for doing decompilation, and I want to kind of emphasize that this is not even really fully decompiled. We're only re-rolling loops here. And so if we had, even more abstractions actually lifted out of the netlist and into the HDL code, we might even improve simulation time more. There's a few other metrics that we evaluate as well, and the details for that are in the paper. Please check it out. So anyhow, to kind of conclude, we established this problem called hardware decompilation. We specifically look at hardware loop rerolling as a first step in that direction. And we've shown that hardware decompiler has value as an actual design tool, given that we can speed up simulation speeds. Going forward, we want to look at more programming abstractions that we have in HDLs and be able to pick those out of netlists and lift those back up. Additionally, since we're using these solve-related techniques, scalability is always an issue here, so we're always looking to find ways to scale these techniques to larger and larger hardware designs. And so that's all I have. Thank you for your time.
All right, so we've got the mic up here in the center, and looks like there's already a rush for it. So you got a question, you better get there soon. Go ahead, Sam.
Cool talk. Did you have any studies of if you synthesize your RTL with different synthesis engines that maybe do different things to your loops, you were still really robust to that sort of variability?
I see, yeah. I can comment on a couple of things related to that. I mean, for one, we only used Yosis for synthesizing. Actually, sorry, we used Yosis for the SystemVerilog ones, and then we used PLDI' as itself to grab netlists from those. So those are two different hardware tools producing different kinds of netlists. And in both cases, we're rerolling loops. With Yosis, we also had optimizations and things that those netlists would go through as well. One thing that was kind of fun to notice, in some of the SystemVerilog benchmarks, some of them did not have loops. Some of them maybe just repeated the steps just 16 times or whatever it was. And so that was kind of a fun opportunity to see oh, we actually found some opportunities to loopify some of the code. Thanks.
Hey, thank you for the talk. So I have a question. So when you look at the software decompilation, there are certain problems that are especially hard, control flow recovery or mapping stack slots to local variables. So what do you think would be a major problems to solve in the hardware decompilations? Sure, yeah.
There has been some previous work generally around reverse engineering circuits, and some of those ideas there I think have some overlap here. I think some of the interesting directions forward are things like state machines. Finite state machines are used a lot in hardware designs, and I think it'd be really interesting to incorporate ways of recovering FSMs and then lifting that back up to the HDL level. So that kind of control and data split is an interesting thing to look at in hardware. Okay. Thanks.
Hey, Zach. Great talk. Thank you. So I just want to channel my ISCA reviewers from this year and really poke at the last bullet you have on the slide. I want to know, like, how big how big was the largest benchmark that you guys tried to scale to? And you said, you have some ideas for how to scale. Can you elaborate on those?
Sure. Yeah. Let's see. The largest benchmark that we have. I don't have we have numbers on the paper, but it's on the order of I think like thousands of gates. Like, it's not huge. So there's a lot of opportunities to really scale up to larger and larger net lists. I think that one was like a couple of the floating point modules that we looked at were the larger ones. I think one of the things that we're interested in is there's been other work in finding module boundaries in net lists. And so I think that can be pretty complementary to what we're doing, because the way that we're treating this is kind of per module, right? So if we can take a larger design, split it up into modules, and then do these kinds of decompilation techniques on a module by module basis, then we can try scaling things up that way. Yeah, thanks.
Hi, I had a question about the performance. I was wondering what the worst case performance is, especially if you had a case where doing your loop rerolling actually resulted in worse simulation performance, or is it guaranteed that if you use the tool, you'll get at least the performance that you used to have?
Got it. So the question is about simulation performance and if we could ever have worse simulation performance. I noticed on our smaller benchmarks, there was not as much of an improvement in terms of simulation time. I think that's just because of just generally the size didn't make much of a difference for introducing loops into the design. So that was one. Let's see. I could maybe see other scenarios where maybe Verilator might be optimized to expect might be better optimized for certain patterns that we don't directly produce from our tool. So that could maybe be an instance, but I'm not too sure.
Thank you.
Thanks.
John Hughes, I'm interested in nested loops, in particular loops where the inner loop bounds depend on the outer loop variable. If I understand correctly, those loops won't be detected the first time you run clone detection, but you should be able to detect them by running clone detection again on the output of the loop reroller. Right. Are there any problems that crop up when you process code that already contains some loops?
Sure, yeah. Unfortunately, none of our benchmarks had, or I think only a couple of our benchmarks had nested loops in them. And so the way that we treated it was just by unrolling the inner one. We definitely want to look at find more benchmarks that have more loop units, more nested loops, and really find ways of supporting that, because it's something we're interested in. Thanks.
Oh, okay. This would be a super quick question.
Yeah.
Okay.
All right. Yeah, so great talk. I had a quick question about dealing with control flow inside of the loop. So if there's control flow inside of the loop, and then once you unroll it, as the synthesizer does, are you able to rediscover that control flow and construct a loop that has both paths in it, or do you construct two independent loops?
Sometimes it depends.
Okay, let's go ahead and we'll stop it there. That's a good answer. Let's thank Zach again.